Welcome back to Daily Dose of Space. For most of human history, the universe was silent. Not because it truly was, but because we had no way to listen. Stars rose and fell, galaxies collided, and extreme events unfolded across unimaginable distances, completely unnoticed. That changed in the 20th century, when humanity learned how to detect not just light, but signals. Radio waves, bursts of energy, faint patterns buried in cosmic noise. Suddenly, the universe was no longer quiet, and almost immediately, something unsettling became clear. Some of the signals we detected made perfect sense. Others didn't. They appeared briefly, vanished without warning, and refused to repeat in predictable ways. Decades later, with vastly better technology, some of those signals remain unexplained. Tonight, we are not talking about aliens, and we are not talking about science fiction. We are talking about real signals, recorded by real instruments, studied by serious scientists, that still do not fit comfortably into our understanding of the universe. When the universe started talking back, the first strange signals were not recognized as strange at all. Early radio astronomy was a messy business. The instruments were crude, interference was constant, and researchers often struggled to separate cosmic sources from human-made noise. In that environment, it was easy to dismiss anomalies. Signals would appear briefly, sometimes repeating, sometimes not, often buried in static. Many were written off as equipment errors or atmospheric effects. This skepticism was not a flaw, but a necessity. Without it, radio astronomy would have drowned in false positives. However, as instruments improved, patterns began to emerge. Some signals were unmistakably astrophysical. Pulsars, for example, produced incredibly regular radio pulses, so precise that they rival atomic clocks. Once identified, they became some of the most reliable objects in the universe. But not everything behaved like a pulsar. Other signals arrived abruptly, lasted for milliseconds, and carried enormous amounts of energy. If these signals originated from distant galaxies, which evidence increasingly suggested, then they were releasing more energy in a fraction of a second than entire stars do over long periods of time. At first, these events were treated as curiosities, rare, poorly understood, and difficult to confirm. But as detections accumulated, one thing became clear. These signals were not artifacts. They were real, and they were coming from far beyond our galaxy. This realization marked a turning point. The universe was not just sending us information, it was sending us puzzles. Signals that shouldn't be possible. One of the most unsettling aspects of these unexplained signals is not their existence, but their properties. Some of them are incredibly brief, lasting only milliseconds. Under normal circumstances, such short signals imply a very small source because large objects cannot change that quickly. But small objects should not be able to release that much energy. This contradiction lies at the heart of the mystery. If the source is compact, like a neutron star, then the energy output stretches the limits of known physics. If the source is large, then the timescale makes no sense. Either way, something does not add up. To complicate matters further, some signals repeat. This alone breaks many proposed explanations. Catastrophic events, such as supernovae or neutron star mergers, can produce intense bursts of energy, but they only happen once. Repeating signals require a mechanism that can survive and continue operating. Even among repeating sources, behavior varies wildly. Some repeat frequently for a time and then fall silent. Others emit sporadically, with no apparent rhythm. Attempts to link their activity to rotation, orbital motion, or magnetic cycles have met with limited success. And then there is the issue of location. Several of these signals appear to originate from environments that are already extreme, such as regions with strong magnetic fields or dense stellar populations. Others, however, come from surprisingly quiet parts of their host galaxies, where nothing obviously violent seems to be happening. The universe, it seems, is capable of producing extreme phenomena in places where we least expect them. At this point, scientists are no longer asking whether these signals are real. The question has shifted to something far more uncomfortable: whether our models of high-energy astrophysics are missing entire categories of behavior. Theories that almost work. Over the years, numerous explanations have been proposed, refined, and sometimes quietly abandoned. Highly magnetized neutron stars, known as magnetars, are among the leading candidates. Their intense magnetic fields can twist, fracture, and reconnect, releasing enormous bursts of energy. This idea fits many observations, but not all of them. Some signals appear too energetic even for magnetars, or show frequency structures that are difficult to reproduce with known magnetic processes. Others repeat in ways that magnetar models struggle to explain without fine-tuning. Another idea involves interactions between compact objects and their environments. For example, a neutron star passing through a dense cloud of material could produce irregular bursts as matter intermittently falls onto its surface. This scenario explains variability, but raises new questions about why such systems appear to be so rare. There are also more speculative proposals involving exotic states of matter, unknown plasma effects, or entirely new astrophysical mechanisms that have yet to be fully explored. What unites all of these theories is not that they are wrong, but that they are incomplete. Each explanation solves part of the puzzle while leaving other pieces untouched. The result is a situation where progress feels real, yet resolution remains elusive. This is often how science advances, not through a single breakthrough, but through prolonged discomfort with partial answers. Why these signals matter. It is tempting to view unexplained signals as isolated oddities, interesting but ultimately peripheral. That would be a mistake. Signals are not just curiosities, they are information carriers. They encode details about physical processes that cannot be replicated on Earth. Ignoring them means ignoring data about how the universe operates under extreme conditions. Moreover, the history of astronomy suggests that anomalies often point the way forward. Pulsars were once mysterious signals. Quasars were initially dismissed as measurement errors. Even the expansion of the universe itself emerged from observations that did not fit existing theories. The signals we still cannot explain may represent new stages of stellar evolution, new behaviors of matter, or entirely new astrophysical objects. They may also reveal limitations in how we interpret data rather than flaws in nature itself. What makes this moment unique is scale. We are now detecting these signals not one at a time, but in growing numbers. New telescopes are coming online, designed specifically to capture transient events. Patterns that were invisible before may soon become undeniable, and yet, for now, uncertainty remains. The universe is speaking. We are listening more carefully than ever, but some of what we hear still refuses to translate. Signals we still can't explain are not failures of science. They are invitations. They remind us that understanding does not arrive all at once, and that even with our most advanced instruments, the universe retains the ability to surprise us. Some of these signals will eventually find explanations that feel obvious in hindsight. Others may force us to rethink assumptions we didn't even realize we were making. Until then, they remain exactly what they are: messages without clear meaning, traveling across billions of years of space, waiting for the moment When we finally learn how to listen properly,